everyone again. I'm really happy to be here as I've been a member of Women Who Code community for almost 4 years already. So I'm like really happy to be at this amazing conference. And first of all, I wanted to share why I'm going to talk about big data and data science and the difference between those two. So I'm working as big data developer, and often I'm being confused for being a data scientist or working with data science and machine learning models. And I think that it kind of doesn't make justice to the role of big data engineers. So today I want to share how these two spheres and how these two professions work together and how they are actually different. So as it's been said, I work as a big data developer at Captify, and Captify is a British product company, and actually it's the largest independent holder of user search data outside of Google. Also, since recently, I am diversity and inclusion ambassador for the Kiev office. And as it's been said, I'm a Women Who Code Kiev data engineering lead. Also, I'm mentoring at our mentorship program, and I speak often. So today I'm going to talk about big data in general, like the concept itself, the main characteristics, how we define big data. Then I'm going to move to the actual difference between big data and data science. And only after that, I can share a bit of practical cases where both big data and data science work together in order to kind of get a more visual perspective and better understanding. So the term big data usually makes people think about the volume of data. So for example, if we have gigabytes of data, it's kind of, maybe it's already big data, but not so much. But what about terabytes of data? Maybe it's like definitely big data, or petabytes is probably even larger. So it's definitely big data. But in reality, it's not that simple. In reality, there is this a paradigm which is called 5 V's, because there are 5 main characteristics that define big data, and volume is only one of those 5 characteristics. So volume defines the amount of data, I would say so, but there is no specific limit by which we can say that after this limit, we can define that it's big data, and before that limit, it's not big data. So we can say that gigabytes of data is definitely big data, or petabytes, because we don't have this limit. But there is some kind of imaginary bound, I would call it so. Imaginary because it doesn't work for all of the cases. So this imaginary bound helps to think that big data is a kind of data that we can process only in distributed way or with distributed systems, because this kind of data cannot be processed only on one machine. And it kind of works in a lot of cases, but it doesn't work in the cases when we have very high performance machines. And as now the performance of machines is getting more and more increasing, it's kind of really sensitive bound. So another aspect is velocity. And velocity means that we work with static or dynamic data. And static data is the kind of data that is not sensitive to specific time period. So we can have huge delays or small delays, for example, 3-hour delay, 5-hour delay until the data actually gets into the system. And in a lot of cases, we don't really care about such delays, because we can, for example, build the analytics over the time period. So we don't really care if the data gets like in the morning to the system, or in the evening, or in the specific second. And in such cases, we work with batch data, because we can not only process record by record, instead we can create batches of these records and process them in series of batches. And another approach, which is concerned around velocity, is working with streaming data. And this is like the opposite one, because we actually work with the real-time data when we process record by record, and the data gets into the system in real time, and we want to process it in nearly real-time fashion. So we want to get the result as fast as possible. And both of these cases define big data, but obviously they have different approaches. Another aspect of big data is variety. And by variety here, I mean formats and data types. And it can be more like general known data types like JSON, XML, or relational databases, or more so-called big data types. It's brought above Parquet and Avro because they are used quite a lot in big data systems. So usually in one project, multiple data types can be used, not only one of those, which is also defined in the big data project. One more aspect is veracity, and veracity in this context means accuracy of the data. So we don't want to work with some kind of dirty data, with duplicates. We want to get the cleanest data possible. And in our case, even the data with duplicates or the dirty data wouldn't like make much sense for the system and for the specific results that we want to achieve. And the fifth aspect, which is the value, is around the result aspect, because we want to set some goal we want to achieve with this data. For example, to count the revenue, to predict the revenue, and we don't want to just have random data sets or like heavily polluted data sets. We want to have like very clean data. We want to have it in a structured manner, and we want to get some sense or value out of it. So as I've said a bit about data formats, there are these main like classification of these formats with which both data engineers and data scientists work. So the first one is like the most famous one. It's a structured data or tabular data format. It's called structured because there are names of columns. We have all the rows structured around those names, and everything is strict in this format. Another kind of format is semi-structured. Semi-structured because we have the guidance in terms of the structure. We already have the names of the columns, and they are defined in a specific format, like tags in XML. But still, we don't have this strict structure of columns. And the third one is unstructured. So instead of having some kind of guidance, like what kind of columns we have, what kind of types, we only have like a lot of tags or images, and we need to specify ourselves how we are going to structure this data. And in terms of processing, I would say that it's the easiest to work with structured data because we have SQL for that, and the hardest to work with unstructured data because we need to work a lot on cleaning up or building some algorithms that would process the data in a specific way for us. So getting to the question of big data and data science. So there is this notion that big data as the kind of data is used by data scientists to build machine learning models. And I would say that this notion is true, but also there is a division between big data and data science in terms of a field or profession, because big data engineers and data scientists work separately and those professions are separate. And now we are going to discover in terms of the like profession, a specialty, some of the features which are different for both of those. And before that, I'm going to introduce a well-known concept of garbage in, garbage out. And this concept provides the understanding why we actually need for big data engineers and data scientists to work together. So when we have a dirty data, as I mentioned, the one which is not structured, that doesn't have much meaning, we can't build actually really relevant and accurate systems or accurate machine learning models out of this data. And before we actually start working with it, we need to have some kind of data pipelines or data pre-processing, which in this case would be the work of big data engineers. So when we have the clean data from the side of big data engineers, we can have a cleaner and more accurate results on the machine learning side. So general machine learning workflow, like very general one, looks like this. We have the data, we build some features, create machine learning model, train it, deploy it, then evaluate the results. And we may run this workflow multiple times until we achieve a specific accuracy. So in this workflow, we can introduce how big data and data science would work together. So we can imagine that we have some kind of flow of data. It doesn't really matter in this case whether it's real-time data or batch data processing. We just have a stream of data flowing into our system. Somehow we just store it into the database. For now, it doesn't really matter how we do that. And after that, the data can be used for building machine learning model, and we will get some kind of metrics or dashboards as a result of this machine learning model. So big data is here on the left side because the data doesn't just get into the database in a magical way, because we need to organize the database itself. We need to set up the pipelines by which the data would flow into the system. So it's like a heavy load work in terms of defining the structure, like reading the data, writing it, and so on and so on. And the data science here would be actually working with pre-processed data, and it may include the pre-processing steps, which are necessary for building specific models. And the main part of this work of data scientists would be actually building machine learning model and maybe gathering some metrics out of it to understand how it works. So we already saw that big data and data engineering here are kind of parts of the two, because they allow to build a more complex workflow, but at the same time, they appear on the opposite sides of the one. And obviously, such kind of responsibilities require different background. Although I consider that you can get into big data engineer or data scientist professions with the same background, it just will require a bit more of time in order to acquire specific skills for each of those. So the main classification in terms of backgrounds for a data engineer, it would be like a map of like an intersection between software engineering and math and stats. Or data analyst, which is the third one, and it's usually this profession means analyzing the results of machine learning models or just the raw data. And for them, the most important intersection would be between math, stats, and data communication. Data communication here means analyzing the data, visualizing it, getting to understand how it looks, like the ranges of values and all of that. And data scientist is kind of in the middle because they need the math, the stats, they look into the data a lot. That's why they need this data communication background, and they still need to actually code the applications, do the features engineering, so they need software engineering skills. But I would say that in reality, these kind of backgrounds are not that even, because usually in all of these circles would be a bit skewed. So there is like data analysts would be closer to data communication than just having like this even intersection, while data scientists would be closer to math and stats and algorithms, or machine learning algorithms specifically. And data engineers would be closer to software engineering in terms of their responsibilities. So let's imagine that someone has a software engineering background. So in order to get to big data engineer or data scientist, they can actually reuse their skills. And in this case, I would say that software engineer background is ideal for big data engineers because the main tool set is already here. It's programming languages, whether it's Scala or Python or Java. That's libraries for working with data, like parsing this data, reading the data from the database, writing it, working with SQL, NoSQL databases. That's all that's necessary for working as big data engineer. While for data scientists, it's kind of useful because it may help with deploying machine learning models and writing better code and just reading the data from the database. But there still would be like needed the knowledge of more like mathematical side or machine learning side as well. And another background, I called it data analysis, but I meant the knowledge of like algorithms, the main statistics, looking into the data, using tools like SAS, Excel, and Tableau, knowing SQL. That's why working with query engines like Google BigQuery, for example, and having some knowledge in programming languages, whether it's R or Python. And this background is ideal for data scientists because they already know the statistics, they know the algorithms, even if they are like not knowledgeable about machine learning algorithms specifically. It's still useful, and they know how to look into the data, how to work with the data and query it. For big data engineers, that might be not enough experience with programming itself if it was only used for like visualizations or some scripting. So here would be like more time needed to learn that in order to become big data engineer. So as we've seen the backgrounds, we can already kind of map what kind of responsibilities both of these professions have. And starting from data scientists, I defined only the main ones which help to describe them in the general workflow. So the first one is data preprocessing, and it usually is needed to just set up this proper structure of the data specifically for some machine learning models, because it's not like in most of the cases, it wouldn't be enough to just read the data from the database. Usually there is still some kind of preprocessing steps or definitely features engineering steps. Another task is data analysis, because data scientists need to look a lot into the data and in order to understand the ranges of the values, some statistical values that would help in actually building machine learning models. And probably the main one of these tasks would be actually building machine learning models. And there is like a huge variety of those. And another important task would be machine learning models tuning, because it actually takes a lot of time for data scientists, and it helps to track their results and actually understand if the machine learning model performs in a good way. And as for the responsibilities of big data engineers, they work with data processing and cleaning. And we can already see here like small overlap between data preprocessing and data processing. But in reality, data scientists would usually do data preprocessing themselves for their machine learning models because they know like better what they need. But sometimes data engineers may be involved in that process as well. And they can process the data or clean it separately as steps of data pipelines that they are actually developing as well, or just separately for some other reasons, whether it's maintainability reasons or just helping out with some machine learning steps. So as I mentioned, developing data pipelines is probably the most important task for big data engineers. And for example, reading that data and getting it into the database can be a data pipeline for that. So there are like multiple types of data pipelines, and usually in one project, there can be quite a lot of those, whether it's like 20 to hundreds of pipelines which serve different data sources and help to achieve different results and different goals. And another task is storing data. But in terms of storing, I mean just defining the schema of data, because data engineers have to do that sometimes, whether it's a query engine or relational database. And probably the least popular and like well-known task is infrastructure, because usually big data engineers considered to be more like software engineers with the knowledge of big data ecosystem. But it's not always mentioned that actually as big data engineers, we have to know a lot about performance of our applications, and we need to understand well how resources are used. And it can also be required to deploy those applications or to deploy some technologies used behind these applications, which is part of the job of big data engineer. So this is how big data engineering stack looks like. Obviously, it's not all of the tools that big data engineers have to work with every day. there are like lots of equivalents here. So there are like multiple programming languages, multiple relational databases, non-relational databases, some frameworks for processing both batch and streaming data, and more like infrastructure side frameworks, like you can see here, Docker and Kubernetes and Prometheus, and cloud services. So usually in one project, we would work with only one equivalent of those. For example, like Python, working with Cassandra and like PostgreSQL database, and maybe some Spark or Kafka, for example. And this is how data scientist toolset looks like. It's a bit different, but we can already see some similarities. So I mentioned here only Python as programming language, basically because it's the most popular, but some people code machine learning models in Java or in Scala, but it's not that widely used. And actually, there are not that many libraries for that. And here are like a set of libraries for both just data processing, features engineering, like pandas and Spatie and NumPy, and libraries for specific fields in data science, like deep learning fields, computer vision, working with time series. And there are tools which are more like, I would say, service and like Jupyter. And of course, cloud services, which are used both with data engineers and data scientists, and they actually may help to kind of connect the two, because we can just set up the whole infrastructure in Amazon, for example, with all the services. And with the help of that, we can easily connect two parts of the workflow. So getting to the practical cases, I'm going to describe in general a bit of cases where big data and data science can be used together. And after that, I can describe a specific two cases with a set of technologies that can be used to solve this problem. And obviously, it's only one of the ways to solve it, because we can choose different alternatives, different tools. Like, it really depends on what we want to achieve. But here I'm just going to show one of the examples in order to just understand the parts of big data and data science and what kind of tools are used for that. So in general, big data and data science work in different fields. First case, we can imagine some kind of a website with traveling information, like searching for the flight tickets, getting some prices, getting some updates when the prices are changing. So for example, having the user data there. So big data science would be working a lot with the amount of data, maybe more like batch data or streams when it's about updates. And the data science side would be maybe building recommendations or just tracking how the data changes. Another case is smart house. And in this case, we can work with streaming data processing. So the data flows from some sensors for humidity, temperature, or tracking of the movements. And on the big data side, it would be important to just process this data, set it up in the proper format, and machine learning models can be built in terms of anomalous detection in order to understand in real time if something is wrong happening in the system. Another very popular case for big data specifically is financial sphere, because in financial sphere, we have to do a lot of reports, especially like yearly reports, quarterly reports, and those require massive amounts of data for processing. So it's not necessarily used with machine learning algorithms. Sometimes it's just only like raw data set up with a better structure for the analytics team or others to use. And another case is e-commerce. And here you can imagine, again, the website with some users' data, their search history, their shopping history, some items that they can buy, and big data engineers would work on actually storing the data, building more performance systems, while data scientists would work on actually building recommendations on the items that were bought by the users. So getting to the cases. First case I'm going to describe is anomalous detection case. So we can get back to the description of a smart house. And here we are definitely going to work with streaming data, but also I think that it would be important to imagine that we have a batch data in the system as well. So we want to check in like historical way that we already had values in the specific range. And if we had those, then it's not an anomaly. It would be useful for building a machine learning model to actually like look back into the history, except for just getting real-time data from the tracking services. And this historical data should be pre-processed and just stored in general by big data engineers. And result of machine learning model would be a simple answer like anomaly or not anomaly or something more complex. So in terms of tech stack, it may look like this. So going from the like higher level of the diagram, we can store the data in Avro format on Amazon S3 storage. It works as a storage system, and big data engineers can just read this data using Spark, and Spark is really widely used in the big data world. And they can read this format easily with Spark and just store the result in PostgreSQL. So the batch data process inside here is done. Lower level here works with streaming data. Let's imagine that we have some kind of API that works with these sensors. And therefore, we can read the data from this API using Play framework, which here is we kind of have a Scala stack mostly. So we would use a Spark streaming module to read the data from Play framework in real time. And then we get to the data science side. So here we have a Prophet framework by Facebook, which is used to build in this anomalous detection algorithm. And Prophet framework here combines the streaming data and batch data analysis. So the batch data comes from PostgreSQL database, and Prophet can read from this database. And also Prophet can work with Spark streaming. So this framework is going to just read the data in streaming format from Spark. And here on that basically step of the pipeline happens features engineering, building machine learning model. As soon as it happens, we need to deploy the model. And here I just chosen Flask as a way to do that. So the Flask would connect to Prophet. And also Flask can read the results, can write the results to the database, which is PostgreSQL. And we can get like results like anomaly or not anomaly in database or more complex description. And then the Tableau as a tool can be connected to PostgreSQL and we can get visualizations out of it. So here the data scientist can just build this model, go through this the whole deployment stage, and the result would be back into the database with a set of visualizations and all the metrics in Tableau, which is like a closed life cycle here. So as I said, it's one of the ways to build such system. Another case that I'm going to describe is going to be oriented around big data specifically, because in reality, we can have separate projects for data scientists and big data engineers. So I've shown already that they work great together, but yeah, we can have separate projects. So for data scientists, usually it would be more research-oriented projects. So they wouldn't need to actually deploy models, or they can do it in a more simple manner. Therefore, they can just not rely on the help of the data engineers or others to do that. And for data engineers, a separate project would be around building more like heavy load systems or pipelines. So here's an example. We may imagine that we have a database in the system and we want to build a data lake which would serve multiple users. So for now, it's not really comfortable for all the users to go to the same database. It gets into this really unstructured system because everyone just pushes the data there, everyone reads it. Not everyone has the same structure they actually need for their queries. So we want to kind of separate that. And we are going to do that with the help of ETLs. And here, as you can see, it's only the data engineers work. We don't have machine learning in here. So the pipeline looks rather simple, but it's like one format of ETL. We have the source data in PostgreSQL database. We are going to read it with Kafka framework. So Kafka is just going to store it in a more reliable manner. And then we will read this data with Apache Spark. Also, you can pay attention that it's a batch data processing job. We don't have to process the real-time data here. And Spark is going to read Kafka and store the data in Hadoop HDFS, which is a storage system very similar to S3. And then we can either like set up Cloudera Impala on top of HDFS, because Impala uses as a storage HDFS, or we can create a separate storage for Impala and just move the data from this HDFS to Impala storage. Impala is a query engine, it's not a database. And then Impala can get easily connected to Tableau, where we can visualize the data and create reports. So this actually very simple pipeline shows that we can have multiple types of users here. We can have users like developers, which can reach out to the database, or they can read the files directly from HDFS in like raw format. Another set of users that we can have is data scientists or data analysts. So they can view data in Cloudera Impala. They can also reach out to the database because some part of the old data would be there. And the third level of users would be business level users. So the ones that don't actually care about the specific like values of the columns, and they would go to the Tableau to just look at the formats, to look at the visualizations, the results of some reports, and so on. So here we have again like this closed pipeline, but this very simple setup helps to actually build a data lake with multiple users and multiple purposes that we can like achieve with the help of these frameworks. So getting to the conclusions, how big data and data science are actually different. So first of all, that I mentioned already is goals. So big data engineers usually have more like maintainability, technical goals, I would say so, because their purpose is to build reliable systems, to serve multiple users, to like help them to do something that they need, like building machine learning models. While data scientists have more business-oriented goals because they try to achieve the same thing the business tries to achieve, like increasing the revenue, for example, but they use machine learning model in this case as a means. They want to achieve the best accuracy to actually reach to this business goal. Another difference is responsibilities, and that's the one that we already discovered. As big data engineers have more responsibilities in like servicing again, building pipelines, storing data, and data scientists have more responsibilities on the side of machine learning models, analysis of the results, data analysis. Another difference is the background. Data engineers should have more software engineering background in order to get these heavy programming skills, because as I mentioned, big data engineers basically are like software engineers and plus the knowledge of big data ecosystem, while data scientists should have more like math and statistics background. And another difference, which I also want to mention, is the results of work. So I would say that results of work for big data engineers are not that visible, especially some changes in their pipelines, because they usually build a stable system which supports everyone and all the other like members of the teams. And that's something like which exists most of the time. And their goals might not be that much visible, so therefore their results of the work might not be that much visible. So again, their results would be oriented around their technical goals. While data scientist results would probably more like be more closely to the business ones, and therefore they would be more visible. because they would like directly influence some goal in the business, like again, increasing revenue. So the results are like the main goal may be the same one, but the ways to achieve it for both big data engineers and data scientists and the things that they are mostly oriented on would be different. So thank you for your attention. Here's my contact info. You can reach out in Twitter or LinkedIn, and here's my